Welcome everybody, and thank you for joining us today for EnSafe's third installment of the Client Education Series webinars. My name is Rich Heinzenberger. I'm a project manager here at EnSafe, and today's topic is titled Machine Guarding, Fundamentals for Auditors and Entangling, and it's presented by Glen Bianchi. Glen is a senior project director here at EnSafe for the Health and Safety Group and works out of the Charleston, South Carolina office. Again, welcome. Thank you for joining us, and I will turn it over to Glen.
Thanks, Rich. Appreciate that. Again, my name is Glen Bianchi. Been with EnSafe for about 12 years, primarily in the health and safety side. Part of that, 18 years in aerospace. And so we're going to talk about machine safeguarding and as auditors and inspectors. Just to adjust expectations here, we're not going to make you a machine guarding expert by the end of today, but what we do want to do is improve your recognition of machine guarding hazards, types of machine guards, and some of the common issues we see with improper use of machine guards. Also improve your knowledge and skills as inspector and auditor, specifically for guarding. So why do we want to do guarding audits and inspections? Well, lack of or improper use of guarding still continues to contribute a significant amount of serious injuries to our workplaces every year. Machine guarding has been and continues to be in the top 10 of OSHA's most commonly cited regulations. And if we are, implement a formal management system like ISO 45001, we're required to assess our legal and other requirements, and this is certainly one of them. So just a quick quiz here. What is OSHA's, in 2020, where did machine guarding land in OSHA's top 10? Okay, actually it was number 10, number 10 on the list this year. So again, continues to be a problem, and here we are, and this data is from 2020. So what are the things that OSHA cites? There's two specific citations that are the catch-all for machine guarding that they're most likely to cite. 212A2 here, and I've highlighted certain things specifically because that's what we're going to focus on. One or more methods of machine guarding shall be provided to protect the operator and other employees in the machine area from hazards. Second one is 212A3II, focusing on point of operation, which is just one area of hazard, but it says the point of operation of the machine whose operation exposes an employee to injury shall be guarded. Guarding device or devices shall be in conformity with appropriate standards. The reason that's highlighted because this now pulls in all those other standards that are out there that aren't OSHA. We know the OSHA standards were written in the early 70s, haven't really changed much and haven't evolved with the technology. So they are quite limited. So this is where we pull in some of the other standards. And again, focus here, prevent operator from having any part of his body in a danger zone during the operating cycle. So as we said, OSHA's the shall do, and there's a variety of other standards here that are the how. Those are the details. And that's where we go to get the fine details of the practicalities of implementing guarding systems. I think only the robot standard is specifically called out by OSHA, but they can certainly use a general duty clause if need be to cite some of the other standards if the citation doesn't fit in one of the two previous citations we just looked at. Today we're going to focus on the fundamentals or basics of machine guarding, conducting audits and inspections, hazard recognition relative to machine hazards. Then we're going to look at the specific types of guarding solutions that are out there, what they're supposed to do, and what to look for during an audit, and what are some of the common findings we see with each type of guard. So I mentioned inspections and audits are two different things here. Inspections typically are done with a checklist to assess specific physical conditions and behaviors. It's not likely to cover all the guarding technical issues, so there's some limitations there. Audits are a little bit broader. They're going to assess things like is the guarding functioning as intended? Audits generally going to rely on somebody having a greater knowledge of some of the technical aspects of guarding to do an audit. May also look at unsafe conditions of the guards, work practices related to machine guarding, improper use of the machine or machine tools, PPE, and some of the other ancillary things that you might look at associated with guarding. So we're doing audits or inspections either, and here we get to some of the fundamentals of doing this effectively, is observe the machine in operation. I struggle with this when doing machine guarding assessments and you're walking through a shop and half the machines aren't operating. Well, it's very difficult to do an effective assessment of a machine if it's not operating. Secondly, talk to the operators. This is a late quite complex and quite dangerous. What materials are they run? What dimensions of parts do they do? What tasks are they actually doing on the machine? And talk about failure modes. What can go wrong? What's the failure mode of that process? Do things break? Can they get ejected? Do they test? So it's for an effective audit or inspection, it's very important to talk to the operator. The other thing that's really important to do is to test the safety control devices on a machine. And I do this and emphasize with permission. I don't advocate any of us as EHS people or people that are picked to do audits to go try and operate somebody's machine. You're going to get yourself in trouble and you're going to aggravate them. So certainly do it with their permission. Have them demonstrate it if possible. And some of the things we're going to look at it, test is, do the interlocks work? Do the e-stops work? Do the presence sensing devices work? Do the two-hand controls work? Because I've seen this countless times. Oh yeah, well, that door has an interlock. Okay, show me that it works. And will it function if we leave the door open? And it's surprising how often that actually happens. So again, another critical part in doing a machine safety assessment, test those safety control systems, make sure they do work. As with any safety work we do, hazard recognition is critically important to do this effectively. And so this next segment is we're going to look at the hazards of machines and caution you to not take hazards and discount them for their potential severity. So that's the point here. And assume the dog will bite. Assume that injury can happen based on that hazard that's there. Some of those hazards, and we'll run through these should be pretty obviously. There's a variety of mechanical hazards, the most common: cutting, friction, abrasion, another cutting or shearing action, impact or crushing hazards. Another less obvious one is ejected parts, tools, or chips. And again, this is important to talk to the operator about how they're using the machine. Metal cutting machine will have very different hazards depending on the speed and feed and tooling and material they're cutting. So it's important to really query about that. More mechanical hazards with drawing in, entangling, rotating shafts, and running nit points. And then there's a whole non-mechanical hazards. And again, go back to, you have to understand what's being done with this machine and this process, because these are the ones that are going to be a little less obvious. And these also pull in other different safety regulations into that machining process on electrical safety, hearing conservation, respiratory protection, HAZCOM, PPE, etc. So as we look at the machine guarding devices that are in place, we want to ask, are these devices appropriate? And each one of these questions is important, based on the task that the operator is performing. Is the guarding appropriate? Is it appropriate for the hazard? The mechanical hazards are going to be obvious. The non-mechanical hazards are going to be a little less obvious, but are we controlling those as well? Are we just restricting access? Are we containing ejected material? Are those guards robust enough to contain that ejected part or do the function that we're expecting of them? Is it appropriate for the need to access the hazard point? Frequency of access is something we're going to talk about with fixed guards or adjustable guards or interlock guards, and what controls we need based on the frequency of access. And the last thing is, guarding appropriate for the operators to actually use it. The likelihood the operator is going to use the guard is based on a bunch of factors. Does it block their view? Does it not fit for some parts that they're trying to run? Is the use of the guard awkward? Is it heavy, or does it present different hazards? A machine guard, as installed, should not create an additional hazard. There has to be an affirmative protection from the hazard that's there. It shouldn't interfere with the process the operator is trying to do, and it should prevent all access to that danger zone. Guarding should provide protection for accidental things that happen, not just normal operations. We talk about that cutter tool that shatters or the part that gets loose and gets ejected. It should not be inconvenient or discomforting for the operator to use it, or definitely won't use it. And it has to stand up to the normal wear and tear of the operation. The other concept that's important when you're auditing and looking at guards is auto. Can you reach around, under, through, or over that guard? Again, this will come up here in a few other ones. This is a press with a light curtain configuration here with a transmitter next to the character in the picture, out to a mirror across the front, to another mirror, back to a receiver on the other side of the press. Well, okay, that kind of sort of protects the front of the machine, sort of, but doesn't protect somebody from coming up on the side and reaching into the point of hazard. So we'll see around, under, through, and over. For the through portion of that, we want to consider the size opening or gap in a guard relative to the distance to the hazard. This comes originally from the table O10 in the mechanical press standard in OSHA, and is also in several of the ANSI standards, including B11, the robot standard, and the power transmission apparatus standard, B15.1, as well as their Canadian counterparts. So this just is, as you can see here, the physical manifestation of that that chart is the gotcha stick here that you can use to physically assess the gap versus distance to hazard. And here's just an example of that, how you'd use it in an extruded metal mesh guard, or you could use it, for a fixed guard that's installed. Can you get around that fixed guard to the hazard? For the reach over portion, we have to go to ISO 13857, and that provides us a table that looks at determining the appropriate height of a guard versus the distance to the hazard and the height of the hazard. There's a company called Proctor Machine Guarding over in the UK that's got a nice little Excel tool that you can download for free on their website that'll help you determine this rather than try it. You plug in your numbers and it gives you an answer. So we're using that sort of situation where we're guarding by location or by distance to make sure we've got the right barrier. And these can be as simple as this with a chain link fence or some other sort of fixed fence. In a case like this, we'd want a locked fence, of course. But this principle of guarding by location or distance. You can also, in addition to the fixed barrier guards, relocate the controls at a distance where somebody's going to be safe. Most common types of guards employed are fixed guards, perfectly appropriate for circumstances where we don't have to access that hazard on a regular basis. Rule of thumb, and I don't think it's any standard, is if you have to access that hazard point less than one time per shift, a fixed guard's appropriate. You don't have to spend the money on the technology for interlocks or something of that nature. What a fixed guard does require is a non-common tool to remove the fastener. So we don't want the average Joe to be able to pull a guard off, be able to pull a guard off. We want somebody that really has the need to pull the guard off and have a specific tool for that. They need to be securely affixed, so they're not going to vibrate or shake loose or move out of position. And we go back to that table 010 or ANSI B11 gap to distance to hazard calculation to make sure they're installed properly. Some of the common issues we see with fixed guarding, we got a variety of things here. We've got guards that have been damaged and now allow access to a hazard. We've got guards that were just designed so that they're not fully restricting access to a belt drive or a rotating disc. We've got guards that are not securely affixed or not robust enough to stand up to the operation and have come loose. And we have guards that have been probably modified by maintenance or somebody that needed access to something and didn't want to have to stop and remove the guard. So these are common issues we see with fixed guards. Another variation on damage to the guard. This is a polycarbonate window on a CNC enclosed machine that's taken a couple hits from ejected parts or cutting tools inside. So the polycarbonate has been damaged. If we see that, we want to note it and have it replaced, because that's compromised the integrity of that polycarbonate window to withstand another impact. Fixed guards are often used for power transmission equipment because, again, they don't need to be removed that often, but some of the issues we see around here are shafts and couplings on pumps that don't get guarded, or the guarding is constructed so that you can get past the guarding. Again, refer back to that table 010 or ANSI B11 and your gotcha stick. Fixed guard around something that, again, is not fully covering that rotating power transmission device, and we have something sticking out, or shaft ends that are sticking out. This particular one, it's a little hard to see, has a keyway, so there's an entanglement hazard there. And the rule on extended or protruding shaft ends, if the shaft extends more than 1/2 the diameter of the shaft, it needs to be guarded. Next class of guards would be adjustable guards. Very useful because they allow flexibility in accommodating various sizes stock material that you're working. But because they require an operator to adjust them, they're subject to improper use. Commonly see that in vertical and horizontal bandsaws where this adjustable guard would be left in the wide open position, so you don't have to deal with adjusting it every time. But it's interesting to note even these other sliding or articulating arm or rotating guards are capable of being interlocked with safety rated interlocks to ensure that they are moved into position when the machine is used. Some of the common issues with adjustable guards is, the operator just doesn't go back and adjust them to the workpiece dimension. This notcher in the middle is the guard's designed to go up and down to the thickness of the part being used, so you have an 1/8 inch gap, but it wasn't adjusted and is left up, and you have more than an 1/8 inch gap. Guard on the left here, this is an error in construction. It wasn't designed and built to fully restrict access. You can reach around the back to this little punch press. And, you know, guards get modified, taken off. This press brake, the OEM guard, was removed and put on this fabricated guard here. You know, on the left side, it's probably not too bad. On the right side, this extruded metal mesh isn't necessarily as adjustable. So there's a gap at the bottom where you can reach into the dogs, which is that crush hazard, or you can reach over it to the shear in the back, which is the cutting hazard. This touches both fixed and adjustable guards. Bench grinder is probably one of the most ubiquitous tools we see around, and one of the most common ones with violations. The tongue guard and tool rest are both part of the guarding system on a bench grinder, and they have specifications, as we see here, to how they need to be adjusted to the wheel as the wheel erodes down during use. Next category of guards is self-adjusting guards. These are, you know, a little bit more reliable because the operator doesn't have to think about using them. They will self-adjust. In this case, we've got a drill press guard here, a table saw guard, and a spiral accordion guard on the lead screw of the lathe. Let's also note that they're missing a chuck guard on this lathe. But these are pretty reliable, less likely to see issues with adjustable guards or self-adjusting guards. But the things we do see is when they're just removed for whatever reason, or they get damaged. And sometimes it's damaged and then removed and not replaced. The next group of guards we're going to talk about are those electronic guards that would be part of a safety control system. And before we talk about the individual types of guards, I wanted to talk about safety control systems overall. This is more of an awareness thing. A safety control system is that interconnectedness of the elements of the guarding. And it's important to keep in mind that a safety control system is only as good as the weakest link. If the components are not safety rated, then the system will not perform to the necessary level of control reliability that gets determined during the risk assessment. Now, doing machine guarding inspection and audit, it's difficult to check this unless you're a machine guarding expert and specifically knowledgeable in the electronic systems of a safety control system. But some of the things we do see, and again, this is on interview with the operator, the maintenance people with the machine, is that perhaps E-stop was wired directly to the on-off circuit and it's functioning as an on-off switch. That's a pretty good indication it's not wired properly as an element of a safety control system. Or the light curtain's wired to the E-stop circuit, and you know the maintenance guy that installed it's going to tell you that. Any of these should have their own dedicated circuit. So the first component we're going to talk about is interlock switches. There's a wide variety of interlock devices for all types of physical environments that you can operate in and all sorts of conditions. That interlocks that interface with the machine control system to prevent inadvertent access to the hazard. It's important to know that interlocks can be linked to other things to restrict access to some of the non-mechanical hazards. So, for example, let's say you've got a laser drilling machine that creates a metal vapor with some toxic metals in it, or a robot that does painting with solvent paint. And before you gain access to that enclosure, you can tie it to a time delay to allow the ventilation system to remove that chemical hazard before you gain access. Or you can tie it to motion. So for example, on a big abrasive cutting wheel or a grinding wheel that may take up to a minute to stop once you hit the off button, you can put a time delay on an interlock to not allow access until the wheel has stopped motion. So interlocks are required when we need regular access to a hazard area for either loading, unloading parts, tool changes, taking measurements of parts during cutting operation, adjusting, scrap removal, maintenance, etc. So frequent applications to get inside a hazard area. You want an interlock, so it's just open, stop, close, restart. And again, these can be tied to any sort of energy source, electrical, pneumatic, hydraulic, or mechanical. So some of the things we see with interlocks, people say, oh yeah, I've got an interlock on the machine. Well, you look at it, and it's one of these simple proximity switches. They do not provide the same level of control as a safety rated interlock. They're easy to defeat. So we can see here, this one's tied back with a zip tie. They're not very robust, so they can get out of adjustment. They're not control reliable. And they're just not equal to a safety rated interlock. So you really need to consider, yes, this machine is 35 years old and came with a simple roller proximity switch, but does that provide the adequate level of protection you need for the hazard? Here's some other examples. As you look, are they safety related? All these ones aren't. It's another simple proximity switch. These are as well. This one on the left, it's hard to see, but there's actually a wire tying that one in place. And it's kind of interesting to see the contact points held in place by 7 fasteners. So the whole reliability of this particular interlock is questionable. As you're auditing, look around the machine. What are the other points of hazard? You can have a nice big modern CNC machining center, and you get back to the tool changer, and is that tool changer door interlocked? Because as the machine's running, this can actuate without notice, and you don't want to be back there swapping out tools while the machine calls for another tool and this rotates. So again, look at all aspects of the machine, all access points, and see, are they either fixed or locked or interlocked? Again, common issues with interlocks, they're not safety related. They've been bypassed either by being disconnected, tied, put in a dummy key for the keyed interlocks. Some of the CNC machines have a keyed bypass at the machine control panel for maintenance or other things. That keyed bypass should not disconnect the interlocks for normal operation of the machine. Next group is presence sensing devices. These are great, provide a great deal of flexibility and ease for frequent access to the applications where we only need to restrict access and we don't have things like ejection hazards or some of the other non-mechanical hazards. We just want to restrict people's access to the hazard point. Presence sensing devices create a stop signal when a person or body part enters the hazard zone. And different presence sensing devices include light curtains or light screens, multiple single beam systems, inline lasers, such as a laser safe system for press brakes, RF capacitance devices to just sense the presence of your body close to a hazard, safety mats, bump strips, or two-hand controls. So anytime we see one of these presence sensing devices, as an auditor, we want to say, has somebody calculate the safe stopping distance? That should be able to be provided to you. And what that is that's that calculation considering the response time of the machines, the safety control circuit, the device, and the depth penetrating factor that's associated with the presence sensing device, coupled with that hand speed constant that's out of the standard to determine what the distance from the hazard that presence sensing device needs to be to stop action in time when the field is penetrated. If a light curtain has been retrofitted onto a machine by the local folks, chances are they haven't done that safe distance calculation, so you really don't know. There are actually equipment out there to use in a situation like that where you can physically measure the stop performance of a machine to validate that the presence sensing device is appropriately positioned. Some of the mistakes we see with light curtains, between the light curtain and that danger zone. Actually, I had a client where that happened, where someone was behind the light curtain in a press and had their hands in the press, and somebody outside the light curtain used the two-hand actuation and actuated the press down. And unfortunately, the individual inside the light curtain had their hands in the danger zone. So you look at that, the configuration of that presence sensing devices, and can we get behind it and then actuate it? And again, we have to consider two people involved in the equation here. Where that's an issue, there are options. You can configure the light curtain differently to cover that whole distance, add a second light curtain or laser scanner or pressure mat inside the light curtain so that nobody can be inside the light curtain. So sometimes it's a combination of devices, but you want to be sure and cover the entire hazard zone and verify that the presence sensing devices are preventing people from accessing the zone. Common issues with presence sensing devices, we go back to that auto, reach around, over, or under. Not going to generally go through a presence sensing device like a light curtain, but here's a case here that we saw, I think, before with the field in front of the press, and we can reach around it from the side. Aerial laser scanners become very popular. They're great, flexible devices, relatively inexpensive to provide a nice safety zone. They typically function as a two-zone configuration where there's a warning when you approach the outer zone, and then a stop function when you hit the inner zone. You could program that field to pretty much any configuration that you can get a direct beam from the emitter. One of the negatives of laser scanners is they do have a slower response time than a light curtain, so it does require a greater safe distance than you would for a light curtain. And they aren't really usable for scenarios where you're going to have dust and chips or water droplets or things like that that would get in the beam field and trigger the beams. So if we see these laser scanners in use, we want to see that they actually cover the entire hazard zone. Again, it's a direct line of sight to the beams, and are we covering the entire hazard zone? Here's an example. Here was a kind of autonomously operating cell, and it was provided with two laser scanners, one here in the back, and you kind of drawn in the representative field that it's sensing, another one in the bottom right corner, which is just out of view, and the field that it's sensing, and again, test the systems. So you can go, obviously when it's not running, you can go in and a light turns on the laser scanner when it is being triggered. So you can move around and verify that the laser scanner is seeing you. In this case, I got inside of this space here and it was not seeing me. So somebody could stand in here, the laser scanners aren't going to know you're in the space. Somebody outside could start up the operation, and this apparatus can slide over into you. The next category is presence sensing mats. These were more common in the past. I think they've really been supplanted by the laser scanners, but they're still out there, usually used in conjunction with something else, but they function by detecting the weight of somebody standing on the mat. Common issues we see with presence sensing devices is, they're movable, so they can be repositioned and allow access to the hazard. They come in these square rectangular shapes, so you're limited on the dimension of the field that you can protect. I've seen these wired to an e-stop circuit, not their own safety control circuit. And they're subject to damage. They really don't like being run over by fork trucks or pallet jacks or have hard, sharp things dropped on them. and some of the older ones are not as reliable. So those are, again, some of the issues we see with safety nets. Two-hand controls. You know, we're proximity to the hazard's important, and we don't have the liberty of the safe distance for a presence sensing device. Two-hand controls are intended to keep an operator's hand out of the hazard during the hazardous motion of the machine. You should be required to keep concurrent pressure on the buttons during that hazardous motion, typically a down cycle, a downstroke. Once the machine makes contact with the part, there's no pinch cross hazard left, and you shouldn't necessarily need to maintain contact. But they do require concurrent hand contact with the buttons to initiate the cycle and contact through the hazardous motion. They should be designed so that you can't, you know, actuate both buttons, let's say with an elbow in a hand and keep one hand free, or tie them down with a clamp. Certainly there's enterprising people who are going to figure out a way, but you know, here's an example where there's kind of a cup around it. They're separated by distance and would be very difficult to defeat. Here's a little bit more modern version down here that requires a finger touch on either side of the switches here. Again, they're protected from inadvertent actuation or defeating. So as I say, an emphasis, test the controls. Here, you know, every time you see two-hand controls, particularly stuff that's been retrofitted to a machine, you want to verify the function. You know, this press here on the right, these obviously came and were designed for that press. I see often, you know, people have retrofitted a couple of buttons on the front of the machine that are, you know, quote unquote, two-hand controls, but then you really test them and they don't function as such. So this little, you know, image shows how you would test and verify. You know, if you press one button, press 1 and 2, it shouldn't actuate. You should have to press both concurrently to initiate the cycle, and removal of one or the other should stop the cycle. Common issues with two-hand controls, and again, I'm emphasizing this, you have to see the machine in operation and talk to the operator about how it's used and the spectrum of uses for a machine. You know, on a press brake like this, I think it's a press brake or a big press, you know, typically it's one person, but sometimes you may be using two people to operate this press. Well, one set of two-hand controls by two people still keeps 2 out of 4 hands available to be crushed, as is damaged, as is indicated here. So again, emphasizing you have to see the machine operation to see how it's used. The last type of guard we're going to look at is the movable barrier guards. These are also good where a presence sensing device safe distance is not suitable, or we need to contain other hazards. I'm not quite sure what this robot is in here, if it's a welding or plasma cutting or plasma spray or painting or something, but there may be those other hazards, non-mechanical hazards that we need to contain and prevent access to. And where we don't have room to swing open a door, these doors, I think in this example here, they roll up and roll down and meet in the middle, or there's ones that just roll up. So these automated movable barrier guards. Some of the common issues we see with these is they create another hazard. For a small, let's say, assembly press fit machine, it may have a polycarbonate door that slides down, that maybe somebody got a little ambitious with the pneumatic actuator and the pressure on it's high, and it creates that guillotine type effect where you can, you know, break a finger or injure a hand if you get caught in there. something like that should have a safety bump strip on it, so that if you do make contact with the door as it's closing, it's going to stop or reverse and go to home. And again, that's kind of the common things where there's some additional hazard with the door that wasn't anticipated. Other hazards with this, poor design, there's gaps that allow access. The actuator's damaged, so maybe it doesn't open or close as fast as it was intended to, and maybe the hazard is occurring before the door closes. I've seen that recently, that pinch hazard with the door itself. All common issues with the movable barrier guards, and you need to see it in operation to sense that. So as we're looking at guards and how guards are applied, how guards are used, these are just some considerations. Again, not necessarily, most of these aren't necessarily tied to a regulation, but just from a functional standpoint. Ergonomics, you want a guard that's not going to require significant force to operate or move. For a bigger guard, that may require some pneumatic assist, lift assist or something like that built into it, or a kind of a shock absorber type thing to allow it to close slowly. Good practice is, identify your guards all the same. Typically yellow or red is going to be a color to make guards stand out. We want people to understand this is a safeguard. We can't operate the machine without this in place. We want to be consistent about that. We don't want guards to create a hazard. In the wear and tear, sometimes they get damaged, burrs, sharp edges, things like that. We don't want to, guards should not contribute to injuries. They should prevent injuries. They should be constructed so that maintenance can still access what they need to easy without having to move the guard if possible, or provide accommodations, perhaps a grease tube out of the guard so you don't have to remove the guard to grease a point, for example. And they should be able to be inspected for function and condition without removing the guard. So keep it simple. So the final piece that we're going to consider here is more of an ancillary safety device, e-stops. E-stops are not considered machine guards, so it's an ancillary safety device. Incorporated in every machine. So I just want to go through the requirements for e-stops and some of the common things we see here. As we walk up to a machine and look at a machine, that e-stop should be easily accessible and located wherever the operator is doing his task. For metal working machines, that's typically pretty obvious. For things like conveyors, you may need an e-stop function along the whole line of the conveyor. Again, where operators are working, they need to have immediate proximity to an e-stop. By design, they should be initiated by a single motion. Push on it. E-stop should override all other functions and operations, no matter what mode the machine is operating in. Important to test e-stops because you want to see how is it reset. That e-stop should have a latching function, so it should require you to pull it out. Usually a pull and turn to reset the e-stop. And then it should require at least one other action to restart the machine. You should not pull that e-stop out and the machine automatically starts. That's an on-off button, not an emergency stop. They must be control reliable and monitored. An e-stop circuit should be its own circuit, its own safety control circuit. By design, red mushroom head button, contrasting yellow background. Doesn't need to say emergency stop, but just that universally recognized configuration of a red mushroom head button and a contrasting yellow background. Probably the most common thing I see in machine guarding is auditing is e-stops without a yellow background. And again, it's typically old machines, and quite often they're right next to other stop buttons, so there is no differentiation between them. And just for awareness, there's different categories based on the function, usually complexity of the machine to consider. But that's more an issue when you're designing the machine to be able to stop safely and not lose restart capability. The other type of e-stop is a pull cord. Some of the issues we see with these is on an older style pull cord, it was a one-way switch, so it had to be pulled, and you'll see sometimes that pull cord is kind of droopy, has droops in the run, and that means if they're still running, that switch is not working properly. The most current modern design is a three-way switch, so you're always under tension with the pull cord. So if the cord is either cut, it's going to shut off, or if you pull the cord, it's going to shut off. And modern ones typically have the reset right there at the home device. So those are some of the things we see with e-stops. So get a red button that's not that's damaged, or it's labeled as an e-stop. It doesn't function as an e-stop. It typically doesn't latch. There's no yellow background. Sometimes I've seen where e-stops have been retrofitted on and they're set up as an on-off switch. They're not supposed to function that way. They're damaged, as in this one is. Or they're located in an area that's not in immediate proximity to the operator. And on conveyors, there may be an e-stop at one end, but you don't have e-stop function along the entire length of a conveyor where people are working. You need to have that protection wherever people are working. So, quick summary for auditing machine safety. Must do: observe the machine in operation. You cannot do an effective machine safety assessment without observing that machine in operation. Talk to the operator to understand how they use the machine, what parts they run, what tasks they're doing. And all of that stuff variously contributes to the hazards you need to guard for. And where possible, test the safety control systems, again, with permission. I'm not advocating you all go start hitting e-stops and breaking light curtains while the machine's in operation. Talk to the operator, get permission. You don't want to ruin their part or ruin their program. You'll have really unhappy operators, but you must test the function of the safety control systems. Remember auto as you look at guarding: around, under, through, and over. Can I access the hazard around the guard? And those questions about, is the guard appropriate for the hazards, for the process, for the task at hand? With that, we're rapidly approaching our hour. We've got 10 minutes here. Do we have any questions?
Present you with a couple of questions here. Here's a question: is there a requirement to periodically test e-stops functionality?
I don't believe there's a direct requirement to test e-stop functionality. It's a best management practice to do it. I don't know of a direct requirement to test it periodically, but that is typical, whether it's an e-stop, a light curtain, interlock on a door, to incorporate, in an operator TPM, once a shift or once a week or something of that nature to verify the function of the safety controls.
All right. I've got another question here.
Actually, I'll stand corrected. The ANSI standard does talk. There's mention of testing e-stops in the ANSI standard, so you can refer there. NFPA ANSI. Sorry.
All right. Do they make do they make control reliable limit switches?
There are a variety of interlocks that function as a limit switch that are safety control or control reliable. So for example, you can use, magnetic proximity switch. There's non-safety rated magnetic switches that would function as a proximity switch, and safety rated, which would be a coded magnetic switch. So you have different poles within the dimension of that switch, so you can't defeat it. So yes, but not the roller switch.
All right. And you referenced the acronym AUTO. Can you remind us all what that stands for?
So when you're looking at a guard, can I reach around, over, around, under, through, or over the guard?
And does that closely represent the expectations from the ANSI standard?
Yes. You have to positively protect somebody from the hazard.
Great. Well, thanks, Glenn, and thank you everybody for joining. I'm sorry about the technical issues we're having. Just a reminder that this webinar and all of our webinars are being recorded and will be viewable on EnSafe's website. Each registrant will receive an emailed certificate of attendance, good for 1 hour of professional development. And I will also be sending a link to a brief survey, 4-question survey, for you to provide us some feedback on this webinar. And any feedback is greatly appreciated. It really helps us with these presentations and to make sure that they're being tailored properly. Again, thank you for joining us, and I hope you can join us for next week. Next week's presentation is Hazmat Training Requirements Responding to Releases. And please feel free to email either Glenn or myself with any questions if we didn't get to your question. Thank you again for joining us, and this concludes the presentation.
Thank you very much.
Thanks, Glenn. Thanks, everybody.